So let's recap first what we reached in our study of transistors since last time. So we stopped at the regions of operations of BGT transistors, NBN transistors in specific. Okay. So, and here is the recap for the characteristics between IC and VCE, the voltage between the collector and the emitter, and the current of the emitter. We said that we have three regions. We have this green dot, just 1 point, okay, but we call it region, in which the transistor has no current. The current is 0. So this is called a cutoff transistor, a cutoff region, and in particular in that region, the base emitter junction will be reverse or off. I mean by off, it might be forward, but the voltage is less than 0.7. Okay. So at that time, IB will be 0 and also IC will be 0. Let's write this down as well. So IC will be 0 as well. So IC also equal to IC equal to IE, because IE is just the summation of both. So if everyone is 0, so IE will also be 0. Okay. Now the second region is called the saturation region. So let's go in order like this from left to right. So the second region is called saturation region, in which both junctions between base and the emitter and the junction between base and the collector will be forward. Okay. In that case, we will assume that VBE is equal to 0.7 because this junction is forward. And the voltage between the collector and the emitter will be 0.2. And nobody asked me why 0.2, why, from where we got this. Okay. If we look at the characteristics here, yeah, you see that's very low. But if you draw the transistor itself, if this is 0.7 and this is forward as well, so forward. If this is forward, so if it's voltage, for example, 0.6 or 0.5, okay, the voltage between collector and the emitter is just 0.7 minus this voltage. So if it's 0.5, for example, which we always assume, it will be 0.2. Okay. That's why, and it might be also 0.6. This junction might be also 0.6. So at that time, this VCE will be 0.1. But we usually assume it 0.2. Okay. So we usually assume VCE is equal to 0.2. And again, IE is equal to IC plus IB. This is just a fact, each time. But now IC divided by IB is less than or equal to beta. It will be equal to beta only at the edge of the saturation. And this edge happens when this junction is 0.4. Okay. The third region, which is called the active region. In this region, IC has no relation with VCE. I mean, it's always constant, whatever the value of VCE. And we have these equations. VBE is equal to 0.7 because junction 1 is forward. Junction 2 is off. It might be reverse or it might be forward, but its voltage is less than 0.4. That's why 0.4 is is a transition point, we can say. So we say that VBC should be less than 0.4 if your assumption is correct. If you are solving some example and you want to be sure that you are really inactive, you should see that VBC is less than 0.4. Again, IE is equal to IC plus IB. That's a fact everywhere. But now IC is equal to beta IP. Okay. And oftentimes, if you are solving some example and you know that the transistor is working in active, then you can say that IE is approximately equal to IC. And actually, it's equal to beta over beta plus 1 IC. But for beta much larger than 1, beta over beta plus 1 will be approximately equal to 1. That's why we usually assume that IE approximately equal to IC. And you will see in the exams that I will solve this is today and maybe next lecture that this is usually very correct. Okay. So let's continue. We take some example last time in which we have here, we take just, very similar example to this circuit, but there was, a battery here with 4 volt. Now, what's happened if we remove this battery? So let's, go back and remove this, not to confuse anyone. So it is the same example that we solved last time, but with no battery near the base emitter junction. And you know that our operation, either in cutoff or saturation or inactive, depends on the base emitter junction biasing. If it's forward, then we are either in active region or the saturation region. If it's off, then we are cut off. This point, the green point that I showed you. Okay, in that particular example, base emitter junction is just a passive voltage. It cannot create its own voltage. There must be a source, just like a diode. It's actually a diode. It's a junction. So it needs a source to give it this 0.7. Okay, and now this source has gone, which was here in last example. So this should be in cutoff. Although I will assume it's inactive, we will see that it's not inactive. I mean, we will get something wrong out of the calculations, something negative, something unlogic, doesn't conform with the active region assumptions. Then we will assume it's a saturation, and again we'll find that this assumption is also wrong. Then it's a cutoff. Okay, so let's solve this. Assume active. And it's very safe to assume always it's active in the beginning. Okay, because, especially with transistor applications or problems, because it's not, it's more complex than the diode. So if we assume it's active, let's make that. Yeah. So VBE should be equal to 0.7. Okay, so here is the 0.7. And remember, the current here is IE. So let's, from loop 1, this loop in here, okay, let's write Kirchhoff voltage law. Again, we will not draw the equivalent circuit. I am training you how to deal with the transistor circuit without drawing the equivalent circuit, because it's easier and it will save you some time. But of course, if you just confused, you can remove the transistor as I showed you last time. So watch the video and put instead the equivalent circuit, which is a junction and a current source. So let's do KVL in here. Okay, so we have here 0.7. So if this is positive, so minus 0.7, and also minus IE RE equal to 0. There is nothing more than this. Only two stuff. We have the junction with VBE, so it's the voltage is VBE, and we have also the voltage across the resistor. I'm sorry. So IE RE equal to minus 0.7. So if this is going the next side, the other side. So IE RE is equal to minus 0.7. So IE equal to minus 0.7 over RE, or minus 0.7 over 3.3 kilo ohms. This is something negative, less than 0. And this is not possible. So whenever you are in active or saturation, and you are assuming the currents in these directions that I'm showing here right now, this current should be positive, just like the diode. The diode, we said that if you are assuming it's on, the current should be flowing in that way, and it should be positive. Same in here. So if you have a current negative, then you have something wrong about your assumption. So the assumption is incorrect. So it's not active. So let's go and assume it's a saturation. Assuming saturation will not change something in loop 1, because again VBE is equal to 0.7. And again, the current flowing through RE is also IE. So again, from loop 1, we have the same. From loop 1, we have the same stuff in KVL. We have again minus 0.7 minus RE equal to 0. So again, IE is equal to minus 0.7 over RE, which is negative, and this is also not incorrect. So based on that, again, our assumption that it's a saturation is also incorrect. So this is incorrect assumption. So if your transistor is not inactive, if your transistor is not in saturation, so it must be in cutoff. It must be one of these, okay? So the transistor must be in cutoff region. So IE equal to IC equal to IB equal to 0. Okay? Okay, guys. So this was, one of the, we will not take much, examples in cutoff, but, I needed to show you that if you don't have, something to give 0.7, some source, some battery, to give 0.7 to the junction here, then the transistor will be cut off. So let's take another example. Again, very similar to the example 1, or even the previous example, example 2. But now we replace, or we put a battery with 6 volt. So example 1, same circuit, but the battery was 4, this battery. Now the battery is 6, okay? So now there is something to give bias to VBE, just like example 1 that we solved it in previous lecture. So probably the transistor will be either in active or saturation. So let's assume active. And by the way, any the question in any problem is just to find the Q point. The Q point means the operating point. Okay, so the question all the time is finding the operating point. Operating point means finding IC, finding IE, finding IB. So let's assume active. That means VBE is equal to 0.7. So from this loop, from loop 1, let's draw Kirchhoff voltage law. So we have this guy in that direction. We have also IE flowing in that direction in RE. So the voltage is in opposite direction. So if we follow this this loop clockwise, so we have 6 minus 0.7 minus IE RE equal to 0. Okay. So okay, so IE equal to 6 minus 0.7 over RE, which is 3.3. Okay, and in these problems, usually the resistors is in kilo ohm. So just keep it in kilo ohm, and the current will be in milliamperes, because the kilo is just 10 to the power 3. So no need to convert it back to ohms just to keep the current in milliohms. So using these equations or these calculations, this will be 1.6 milliamps. Okay. IC approximately equal to IE. Okay. Or if you want to calculate it exactly, it will be exactly 1.568 milliamps. Very close to 1.6. That's why we usually just assume that IC equal to IE. Okay. Now let's calculate, because we assuming it's active. So this junction here, the BC junction, the base collector junction, should be off, reverse, or the voltage VBC less than 0.4. Let's check that. So let's calculate VC, the voltage at that point. Remember, the current IC is flowing in that direction. So VC is equal to 10 volt minus IC RC. So this will be equal to 10 minus IC, which is 1.568 milliamps, multiplied by 4.7 kilo ohms. And you know, kilo will be, cancelled with milli. So don't, again, just to keep resistors in kilo ohms and keep the currents in milliamperes. That will make your life very easy with these questions or these problems. Okay, so if we calculated this, VC will be equal to 263 volts. Good. What is VB? VB is the voltage at that point, which is, very clear. It's equal to 6 volt. So VBC, which should be less than 0.4, is equal to 6, which is equal to, let's do it very, very detailed. Equal to VB minus VC. VB is 6 volt and VB is 263 volt. That is equal to 3 point something. 3, it's, or 3 point, I think 47, something like this. 3 point something, whatever it is. Okay, and that's not less than 0.4. VBC should be less than 0.4 because the junction should be off. So our assumption is incorrect. So the assumption, which is active region, is incorrect. So let's assume saturation region. In saturation, it's still VBE assumed to be equal to 0.7, but we showed that VCE should be around 0.2 or something. Okay, we will always assume it's 0.2. Just to be on the same page. Okay. So now, based on these two givens, we will calculate IC and IB and IE. Then we, for the check, we divide the IC over IB. It should be less than or equal to beta. So let's do that. Again, from loop 1. IE RE plus 0.7 equal to 6. This will not change. This will not be affected. So again, IE equal to 1.6 milliamperes. But now you can't say that IE is equal to, IC is equal to alpha IE, or or approximately equal to IE. You can't say so. Because now IP or IC doesn't equal to beta IP. Or it's less than beta IP. Let's do it in more formal way. Less than or equal to beta IP. It might be equal at the edge of the saturation, but generally it's less than. So you can't say that IC approximately equal to IE. This is not valid anymore. This is only valid in active region. Okay. So let's go back and see how can we calculate IC. Okay. We know that the voltage now is this voltage VCE is 0.2. And we know IE. So how about doing this very big loop, this outer loop here? I know it's not, it might be not, very visualizable for you. So let me draw again the circuit. And so this is our original circuit. Here is a 6 volt. Here is something, this point or this node has a 10 volt. So let's draw it as a battery. And this is RE, this is RC, and the voltage here is 0.2. And here is IC, which is unknown, and here is IE, which is now known, 1.6 milliamps. And the RE and the RC is known. This is 10 volt. So in this loop, loop 2, everything is known except IC. So from the outer loop, now from loop 2, 10 equal to IERE plus 0.2 plus ICRC. 10 equal to IE 1.6 milliamps. RE is 3.3, I think. Yeah, 3.3 kilo ohms. And IC is unknown, but RC is known, equal to 4.7 kilo ohms. Don't, convert the kilo to just ohms. Just to keep it in that way, and IC will be in milliamperes. So by calculating this, IC will be equal to 0.957. And this is very clear now that IC doesn't approximately equal to IE. IE is 1.6 and IC is 0.95. It's 30% lower. Only in active region IC approximately equal to IE is valid, but here no. IB, we know that IE equal to IC plus IB. So IB, which is now not known, equal to IE minus IC. So let's subtract 1.6 minus 0.9. This will be 0.64 milliamperes. Now let's check if we are correct or not correct, if our assumption, which is saturation, is good or not. So let's do that. Let's divide IC by IP. IC is 0.957. IB is 0.64. Both are milliamperes, so you don't need to convert anything. This will be 1.5. Remember, beta is equal to 100. This is much, much, much smaller 100. So the assumption is correct. Okay, let's go and take another example. I will take a very, many examples today and tomorrow as well in the lab. We'll take a very small lab. Okay, and we'll continue examples because I want you to practice a lot. So when I publish an assignment and in the final exam, you have enough practice to solve the questions. So let's do this very simple, very simple. This is the simplest, circuit you will see in transistors. Okay. So again, you know, before going into, is it cut off? It's not cut off, basically because there is, you know, a battery here, 5 volt, which is, you know, enough to give the 0.7 to VBE. So it's either saturation or, you know, active region. So let's assume active again. And again, the question is the same for any, you know, for all the circuits that we solve it. Find the Q point mean the operating point. We call the operating point Q point. Usually because we refer to transistor in the circuit as a Q, they call it Q. So usually they give a symbol which is Q capital to the transistor. So if you have many transistors in your circuits, you call, for example, transistor 1 as Q1 and the second transistor Q2 and so on. But this is just a naming, so don't confuse yourself. So assume active, so VBE is equal to 0.7. So let's do Kirchhoff again here in loop 1. So 5, and IB is flowing in that direction. Always remember the directions of the current. IB is flowing into the junction, IC is flowing into, and IE is flowing out, because IE is always equal to IE plus IC. So this is the voltage on RP. So 5 equal to IP RP, because it's opposite direction, so it's in the other side, plus 0.7. Or you can say 5 minus IB RB minus 0.7 equal to 0. This is the 0.7 here. So IB equal to 5 minus 0.7 over RB. So let's solve this. Where is the numbers? Yeah. So this is 4.3 over 100 kilo milliampere. I didn't, you know, substitute or get the final value, because I know that beta is equal to 100. So IC, which is equal to beta IP, 4.3 over 100 multiplied by 100. So this, you know, will cancel each other. So 4.3 milliamperes. So it's easier now to get, you know, without calculator or something. Okay, so now let's calculate, and of course IC is just, you know, IE is just equal to IC plus IB. So, you know, you can calculate it. But what's important is calculate VC to check that really you are in active region. So VC is equal to, remember IC is flowing in that direction, so the voltage in upward. So VC is equal to this point, which is 10 volt, minus the voltage across the resistor, which is IC RC. 10 minus IC is 4.3 milliamperes, and RC is 3 kilo ohms. Again, the kilo will be cancelled by the milli. This is multiplied by 10 to the power 3. This divided by 10 to the power 3. So they will cancel each other. So this will be equal to how much? 1.4 volt. How about VB? So this is a check step. Now VB. VB is the voltage at that point. We know this is based on the assumption that it's active. This junction has a 0.7. So VB is equal to 0.7. Or it's greater than this point by 0.7. This point is 0. So this is 0.7. Now VBC, which should be less than 0.4, equal to 0.7 minus 1.4 minus, it's equal to minus 0.7. So it's less than, of course, 0.4. Actually, the junction now is reverse, which is much better. We need an active region that the junction to be, you know, strong off. And if it's in reverse, it's really strong off. So this was very simple example, as you see. Okay, and I just gave this example to solve the other one, which is much harder, which is this one. Now this is much more complicated. Okay, we could solve. So let's draw it in another way. Let's draw it like this. We know how to solve, you know, the circuit if it's simple like this. This is what we said in last example, right? So what is the difference between this one and this one? The difference lies in this part here. If we convert this part that I'm encircling right now to a resistor series with a battery, then we can solve our circuit in a very easy way. Okay? And that's what we will do right now. So, you guys remember Thevenin and Norton? Thevenin equivalent? You know the first assignment in chapter 1 that I gave you? Okay? So this was, you know, a Thevenin equivalent. So we're gonna get the Thevenin equivalent of that part. So get the Thevenin equivalent of that part. If we get the Thevenin equivalent of that part, we'll transform this circuit in something like this. So let's write it down. Let's draw it down. So let's draw. So when we get the Thevenin equivalent, it will be something like this. So this part will be converted into R Thevenin and V Thevenin. And the rest of the circuit is just the same. So I will draw it just the same. No change. Okay. So this is the idea. This is, you know, a more complex circuit. And one of the solutions, by the way, we'll solve it in 3 solutions, using 3 solutions. So one of the solutions is using 7, just to convert this part, this complex stuff here, this voltage divider portion of the circuit, into its equivalent R7 and V7. So let's do that. Let's do this, you know, and of course to do that we should get R7 and V7. So let's draw that part by itself. So this 15 can be drawn as a battery. This is RB1. This is RB2. And these are the 2 points that we are getting our equivalence. So let's call it A and B. This is A and this is B. These are the 2 points that we are getting our 7 equivalent. Step 1 to get your Thevenin equivalent is to get R Thevenin. To get R Thevenin, you look for between the 2 points, okay, and you cancel any source found in the portion of the circuit that you are getting the Thevenin equivalent to. To cancel a voltage source means you cancel its effect. So what is the effect of a voltage source? A voltage source makes a voltage difference between this point and this point, between its positive terminal and the negative terminal. So to cancel its effect, both terminals should have the same voltage. So we short, so cancel the 15-volt battery, make it short. So we just make a short like this. So now this voltage, there is no difference between this terminal and this terminal. So if there is a current flowing in that direction here, it will be divided parallel between RB1 and RB2. So this circuit will be converted to something like this. This is A, and this is B. This is RB1. This is the ground, and this is RB2. So if you look in this direction, what you're gonna see, what is the equivalent resistance? It is RB1 parallel to RB2. So this is equal to, we know the values of RB1 and RB2, 100 multiplied by 50 over 150, it will be 100 over 3 kilo ohms. That's very nice. This is the first step. Second step is to get V7. Step 2, get V7. Now there is no cancellation of the sources. So we have the original part as it is. This is A and this is B. This is RB1. This is RB2. But we will assume it's open circuit. So assume here open circuit. Assume open circuit between A and B. This is number one. Number two, V7 is actually VEB. It's a voltage between A and B. And simply, if there is open circuit here, then the current will be flow, in series. RB will be in series with RB2. So this means also RB1, RB2 are in series actually. So VEB, which is Thevenin, will be equal to, this is a 15 volt, 15 multiplied by RB1 over RB1 plus RB2. 15, 50, 50 plus 100. So this will be 15 over 3, 5 volt. Basically 50 over 150 is 1 over 3. So 15 multiplied by 1 over 3 is just 15 divided by 3, which is 5 volt. So we get R7 and we get V7. So safely now we can redraw our circuit. Here is RE, here is RC, and both are known. Here is the 15 volt. And now we can put safely R7 and V7. This is 5, and this is 100 over 3. And E is 3 kilo ohms, RC is 5 kilo ohms. And now we can solve the circuit. Okay, so let's solve it. So assume active. All the previous steps is just to simplify the shape of the circuit, to make it more doable with you. So assume active, and now use this circuit instead of the previous one. So VBE equal to 0.7 volt. We have 0.7. And from this loop here, this is IE, this is IB. So from this loop, V7, which is 5 plus, equal to. From loop 1. V7 equal to IB R Thevenin plus 0.7 plus IE RE. Remember that in that region, active region, IC is equal to beta IP. So IE is equal to beta plus 1 IB. Please review the equations of active region. You would see that IE is equal to beta plus 1 IB. They are all related, okay? So this is equal to IB R Thevenin, which is known, plus 0.7 plus beta plus 1 IB RE. So RE, I'm sorry, not RB. We have only one unknown here, which is IB. So from this equation, IB is equal to what? Equal to 12.78 microamperes. Usual IB is very small. Okay. Then we can calculate easily IC. IC is equal to beta IP. So it will be 1.278 milliamperes. Beta is equal to 100. I forgot to mention this. Yeah. Now the moment of truth. So let's check if it's really active or not. So we should calculate VC. So VC, let's go to another, no, let's do it here. VC is equal to 15. So IC is flowing in that direction. So the voltage drop in upward. So VC is equal to this point minus the voltage drop minus ICRC. IC is known, RC is known 5 kilo ohms. So VC is equal to 8.61 volts. How about VB? So VB, which is the voltage of that point, you can calculate it in many ways. You can calculate it as 0.7 plus IERE or IB R Thevenin plus 5 volt. You can calculate it in either way. So I did it using 0.7 plus IERE. Equal to IE, we get it. IE is actually approximately equal to IC. In active region, you can assume this. You can assume that IE approximately equal to IC, or you can just divide, add them together, that's fine. So, I don't remember I did it. Okay, I didn't calculate it, so calculate yourself, but I did then VBC, which is VB minus VC. VB is this value. This is known because IE is known, RE is known, and 0.7 of course is known, and the VC is 8. So this will give you minus 4.037 volts. Okay, and this should be less than 0.4, and it is less than 0.4. So the assumption is correct, which is active region. Any questions, guys? Is there any step here that is not clear for you? Any step? I can repeat whatever you want. Don't be shy.
Can you repeat the open part?
Okay, it's a V-Thevenin, right?
Yeah.
Okay. So to get V-Thevenin and R-Thevenin, we do, let's talk in more details. So for R-Thevenin, okay, what you do, you imagine that there is, a source between A and B. You imagine a source like this between A and B, okay? And you cancel any other sources. So to cancel a voltage source, we make a short. To cancel a current source, we make it open. Okay, this is a voltage source. Okay, it's a 15 volt, this battery. So we make short like this. Okay, so basically RB1 is between this point and the ground, and the RB, sorry, this is RB2. And the RB1 is also between this point and the ground now. So they are, and here again, this is the imaginary, source, something in our mind. So as we see, between A and B, RB1 and RB2 are parallel. So R7 is a parallel combination of them. Now for the second part, which is getting V Thevenin, we make some assumption as well, like the first part. The first assumption that between A and B is open circuit. Okay, no source. This imaginary source, the green one, is not there. So it's open now. Okay. And your V7 will be the voltage between A and B. So since it's open, so the current flowing that comes from the 15 will flow in RB2 and RB1. So this should be RB1 and this is RB2. I am very sorry for this. And again here, RB1, RB2. Okay, and this should be RB2, which is 50 kilo ohms. Okay, so this is open between A and B. So RB1 and RB2 are series. Okay, so voltage divider. If you have a battery connected to two resistors in series, so the voltage in any resistor is equal to the battery multiplied by the resistor over the addition. So the voltage on RB2, this voltage here, is equal to the main voltage, the battery voltage multiplied by RB2, which is 50, over RB1 plus RB2. Or you can do it another way. You can calculate I, which is equal to 50 divided by RB1 plus RB2. And then VAB, which is RB2 voltage, is equal to I multiplied by RB2, which is 50. Okay? You get it, Arsenio?
Yeah, that green battery you put in or current source made it easier to understand.
In the first part, right?
Yeah.
Okay. And you get the second part as well? This was your main question.
Yeah.
Okay. Any other question, guys? Let's do it in another solution. Okay. So let's avoid this 7 and Norton and the stuff. So let's assume that there is draw and green. This is, for example, I1, and this is I2, and this is IB. We know that for sure. This is Mr. IC, and this is Mr. IE. Okay. So we know that I1 at this node from Kirchhoff current law, at this node here, I1 is equal to I2 plus IB. This is equation, but in 3 unknowns. All of them are unknown for us. So we need another 2 equations. Good. So let's encircle this somehow. And continue our solution. Now, from loop 1, let's write it down. Let's write Kirchhoff voltage law for this loop. Okay. The voltage on RB2 is in that way, that direction, because I2 is flowing downward, so the voltage will be upward. And again, we forgot we are assuming active, so assume active as usual. Actually, it's active, we know that because of the first solution. KVL, so it is 0.7. And IE is flowing downward again, so the voltage will be upward. So if we follow this direction here, so we have I2 RP2 minus 0.7 minus IERE equal to 0. This is clear or not? Anybody has a problem with this Kirchhoff voltage law loop? Anybody is following this? So the again, the voltage on that resistor RB2 minus 0.7 minus the voltage of RE, and that's it. Nothing there, nothing, no element there other than these three elements. We know that IE in active region equal to beta IP, I'm sorry, beta plus 1 IB. So I2 RB2 minus 0.7. Let's remove IE and put IB instead. So minus beta plus 1 IP RB equal to 0. Call it number 2. Is there any additional unknowns we are adding? No. So we have the unknowns here. 2 unknowns, IB and I2. RB2 is known, 50 kilo ohms. Beta is known, equal to 100. RB, RM, this is RE, I'm sorry. This is RE. 3 kilo ohms. So let me make it more clear. RE and IB. Good. So here is another equation that we can use. Let's do it in red. To make it more visualizable for you. So we have now 2 equations. That's very nice. We need only one more equation. How about this loop here? You know, this outer loop, we call it. So to make it more visualizable for you, let's draw the circuit again and waste some time. That's fine. So this is the battery here, the 15 volt. This 15 volt battery. I will draw the actual battery. So it will be something like this. This is RB1, this is RB2, this is I2, this is I1. And here is loop 2, the outer loop that I was talking about, just to make it more clear for you why it's a loop. Yes, it's a loop. A loop starts from one point to another point, to the same point, I'm sorry, again. Good. So let's now write down the equation for this loop, KVL for loop 3. Or loop 2, I'm sorry, loop 2. Okay, so 15 equal to, this guy is going downward, so the voltage is upward, again upward. So 15 equal to I1 RB1 plus I2 RB2. This is number 3. 2 unknowns, I1 and I2. Now we have 3 equations in 3 unknowns, IB, I1, and I2. So let's encircle this again here. So by solving, and they are linear equations, it's not hard. By solving equation 1, equation 2, equation 3. So I will write them down for you. You know, where are they in their final form? Yeah, by solving them, I1 equal to .104 milliamperes, I2 equal to 914 milliamperes, and IB is just a subtraction, 12.7, exactly the same microamperes. So if you just confused by the Thevenin and the Norton and stuff, so you can use this question. Also in the exam, I may ask for the Thevenin equivalent. Okay, because it's really a cool solution. Okay, and yet there is another, more simple solution for this problem. So we have till this moment 2 solutions with 2 different ideas for this problem. Now let's have another solution. So solution 3. Solution. Am I writing it right? Solution 3. But this is approximate one. But it has a solid background. Now let's see, the results of this previous solution, the second solution. I1 is 0.1 and the I2 is 0.09. It's very close to 0.1, right? I1 and I2. You will notice that whenever you are working in the active region, usually IB is very small. So we can assume that I1 approximately equal to I2. So here we have I1 equal to IB plus I2. So if we neglect IB, I1 will be approximately equal to I2. So this came from I1 equal to IB plus I2. If we neglect IB, I1 approximately equal to I2. Okay? And then, if we did that, so VR B2, the voltage on RB2 will be equal to 15. It will be voltage divider. لو سمحت روح اطلع بره. لو سمحت روح اطلع بره. Will be 15 multiplied by RB2 over RB1 plus RB2. Because again, if you neglect IB, this will be like a series. RB1 will be approximately in series with RB2. RB2 is known, RB1 is known, again RB2 is known, and 15 volts is known. So then VRB2 is also known. So from this loop here, you will see that from loop, let's call it, draw it again here. From loop 1, VRB2 equal to 0.7 plus IE RE. VRBT is VRB2, we just got it, so it's known. 0.7 of course is constant known. RE is known, so we can calculate IE from this. So IE will be equal to where it is. Yeah, 0.766 milliamperes. IC again approximately equal to IE. And IB, we don't need IB, we just need VC. Okay, VC is equal to, you can of course calculate VB, IB is in a very simple way, just divide this by 100. VC will be IC will be 15 minus IC RC. Again, this is VC and this is IC flowing in that direction. So the voltage in that node is equal to 15 minus the voltage drop over RC. VB is actually equal to VRB. This one. So you have VC, you have VB, you get VC, VBC. VBC would be equal to minus 6.2 volts. And that, you know, since it's less than 0.4, the assumption is correct. Okay. So there is a caveat here. The caveat is that if you compare the results, they are not that close. Maybe there is a 20% error or something, maybe more. Okay. But it's a very, you know, very simple. You will not waste your time. You will not solve a linear system of equations, 3 equations and 3 unknowns. You will not do the Thevenin equivalent. Okay. But the marginal error is big. It's around 20%, maybe more. But we found that it's in active region still. Okay. So don't, if I give you a problem, okay, or even a problem, don't try this solution until I tell you to do that, until I ask you to, you know, to neglect the IB, so then you know the consequences.
So when would you be using, so when is it appropriate to use solution 3?
Practically to get very simple. So practically when you start your when you start, you know, with paper on hand, when you start solving or design a problem or design a circuit or something, okay, and you found that it's really hard to get it using in a very short time using a paper and a pen, then you start make approximation. This is usually in any engineering problem. If you wanna have some estimate, you know, have an idea, at least just a simple idea, just a simple estimation about the operating point of the transistor or the circuit that you are solving, then you start doing approximation. One of these approximation is to neglect IB if it's really in active region. Okay. I'm just giving you that for you know, to help you in your life. But if I want to ask you, I will say explicitly you neglect IB or something, okay, or whatever approximations that I will make. But you go by default, you go with the first solution and the second solution. Okay, guys, anything not clear? You know, again, don't use this one until I tell you to do so, to neglect IB, I mean.